In the name of God, the compassionate, the merciful. Engineering Plasticity, Chapter 5, Plastic Analysis of Bending, Part 10. Continuing with the collapse load idea, I'm going to solve a metal forming problem here. It is called bending in wide ring cogging. Okay. One of the processes that we make seamless rings or cylinders in the industry is called ring cogging, and the process works like this. You see, we have this ring here and we have these punches. Okay, that is the punch and this another punch. These punches, as you can see, insert the load P on the ring like that. So they press the ring and the ring expands, and by expanding the ring the diameter increases and the ring becomes bigger. So if you have at the beginning of the process you have a very thick and small diameter ring, and then you use this process, press it like this many times. We press this many times, and this ring also rotates. We rotate the ring and press it so that the diameter of the ring expands and you get a bigger ring with a thinner section. Okay, the section at the beginning is cross-sectional area is big. As we continue the process of pressing the ring and rotating the ring, the cross-section becomes smaller. Here I'm trying to show you the ring cogging process. As you see, the ring is rotated and it's this punch is punching it. So why we say bending? Because if you look at this ring, when you press the ring, what happens to the material? The material is pushed that way. Let me just use my pen here. The material is pushed that way, like that, and that way. Okay, it's difficult using mouse to draw straight lines. So the material moves that way. When you push it like that, the ring expands. So when you do that, we can consider half of the ring like that. So when we push it like that, there is a force also from here. There's a force there as well, force there. So it is like we can assume or imagine that is a beam. It's a beam, and under these forces it acts like a bending. Okay, so what we have here is this load P acting on this punch with the width of B, and also this load P acting on the punch. The radius of the ring at this stage is R, and the thickness of the ring is H, and also here we can see the cross section of the ring, which is a rectangular cross section. So this PB is the force acting on the ring cross section, and this is also the other dimension of the cross section of the beam. Okay, now here we are saying that W is much greater than H. What is W? W is the width of the ring, H is the thickness. So W is the dimension perpendicular to the screen here. Okay, so W is much greater than H because we say it's a wide ring. Okay, And then, so you can see that if we are pushing the material that way and pushing the material that way, both of these materials come over here and are pushed together at this cross section. At this cross section, we get the plastic hinge. Okay, we push the material moves. Of course, P must be increased to such an extent that the material yields and deformation occurs. So that is the mechanism of this process. You must press the ring to such an extent that it deforms. Now deformation starts from here, because material wants to move that way, and it wants to move that way, but it cannot move. So here we have the highest tension and the highest pressure, and plastic hinge or complete plastic yielding occurs here. Okay, like that. What we have written here is this sigma times h times w, because we have this sigma here, as you can see. It is the stress caused by this load. So this stress times the area. What is the area? Cross-sectional area of the beam is h times w. W is width, h is thickness. And we said that w is much bigger than h. And so that is the force, okay? That's the force. Force times 2r, okay? Because we have this force here times 2r is the diameter, because we say plastic hinge happens here. So that's the bending moment, okay? That is the bending moment which causes the plastic hinge. And it is equal to what? It's equal to, here you can see that WH squared y over 4. In fact, is this relationship that we obtained before. W is B here, h squared y over 4. So that's the complete plastic moment, bending moment, and we have put it equal to this virtual work that we have here, and just like before. And we get this relationship, sigma is equal to h y over 8r. You can see we have obtained this sigma very, very simply from this plastic hinge idea, and of course here you should recognize where the plastic hinge is, otherwise you don't get the right answer. And also, if we use the Tresca criteria, yield criteria, we could write sigma 1 minus sigma 3, the principal stresses, the biggest and the smallest, is equal to 2k. And here obviously everything is negative, I mean, because we are putting pressure on the ring, and our that is minus p, putting pressure. I forgot to say that this p is the load, is the pressure, and here we have multiplied it by b and multiplied by w gives us the force. Now instead of sigma 3 that way, we have put minus p, and instead of sigma 1 we've put minus sigma, because it's compressive. That is compressive and that is compressive. So we get here minus sigma minus p is equal to y. 2k is equal to y. And if we put here for sigma, from this relationship we get p over y, 1 plus h over 8r. So we get p. Yeah, the pressure needed to press the ring in order to deform it. That's what we want. You know, in metal forming processes, we need to find out what load we need to deform the material with a certain geometry. Here we have got everything. got the geometry, the material, the yield criteria, and we have used these all together to get the load required to deform plastically the ring. Okay, so if you have a ring of certain dimensions h and r and w is wide enough, then you can use this relationship to get p required for deforming the ring. Okay, don't forget that here we have assumed complete plastic deformation, and we have assumed that it's a rigid plastic, so that no strain hardening is taken into account. So the P that we obtain is for incipient yielding or a start of the deformation, and we are assuming that as the deformation occurs, there is no change in load because there is no strain hardening. So the material does not become harder. Note that here when we say that wide ring, why we say wide, these equations and why are they applied only for wide ring? Because when the ring is wide, the dimension perpendicular to the screen is greater than h, much greater than h. When that case happens, the flow of material is only in the plane of the screen. Okay, it's only in this plane here. The material can flow only in here. It cannot flow perpendicular to the screen when the ring is wide, because that width gives us enough material so that the material in the width is some kind of like a rigid material, you know. It doesn't let the material move perpendicular to the screen. Or in other words, for the material, because we are pushing the material in here, applying this load, the material must flow because it has reached its yield point. So which direction does it flow? In a direction which is easier. So the material flow that way, because it cannot flow perpendicular to the screen because that is thick, you know, in the dimension in perpendicular to the screen is thick because it's wide, and therefore it's difficult for the material to flow that way. So it's easier to flow this way, and that is what happens. But when this W becomes smaller, okay, not very much bigger than H, then the material also flows perpendicular to the screen and also in this direction as well. So in three directions, X, Y, and Z. But here only, for instance, X, Y, it cannot flow in the Z direction. Okay. Another thing to note in here is that this dimension H relative to 8R is very small. I mean, this fraction is very small, okay, relative to 1. So we can disregard this, and P over Y is equal to 1 for most cases. So P over Y is equal to 1. That means that P must be equal to Y. You can see that we reach a very simple relationship for our process, and then we know what kind of load we should apply to it in order to deform the material and proceed with the deformation and forming this ring.